Hi, welcome to Chapter 5, Overview Part 4, where we're going to discuss Hess's Law, enthalpy of formation, and bond enthalpies. So before we could just jump in, let's define a few terms that you might hear throughout this chapter. And a lot of them are different types of enthalpies. The first one is enthalpy of vaporization. And you might remember this from your Chem 1 days, delta HV. This is the enthalpy needed to change from a liquid to a gas. Then you have the enthalpy of fusion, and that's the enthalpy needed to change from a solid to a liquid. So if you remember when we did states of matter in the heating curve for water, we use these terms. The enthalpy of combustion, sometimes it is with a C for combustion, is the enthalpy produced when combusting a substance with oxygen. The enthalpy of formation, or you could call it the heat of formation, these are interchangeable, is how much heat it takes to form a compound from its elements. Sometimes you'll see something called the standard state, and that means that your substance is in its pure form at 1 atmosphere, 25 degrees Celsius, or 298 Kelvin. And if you have a standard enthalpy change, you put this little 0 up here for standard. So that's the enthalpy change that's occurring at 1 atmosphere and 25 degrees C. So let's talk about our standard enthalpy of formation. So standard enthalpy of formations are normally measured under standard conditions, which we discussed in the previous slide, but it's 25 degrees C and 1 atmosphere. They are a measurement of the formation of a compound. So you're forming a compound from its elements. And they are for 1 mole of the substance. So your units will be in kilojoules per mole. The symbol that you use is this delta HF with the little naught on it. That naught means a little 0. So that's your standard enthalpy of formation. And if you look, here are some examples. So you have your elements that are in your compound producing the compound. And it has to be 1 mole of the compound. So say you balance your equation and there is a number that is not 1 in front of the compound that you form. You have to divide by that number to get it to be 1 for the compound. So here we're looking at the standard enthalpy of formation for carbon dioxide. So when you rip this apart, you're mixing carbon and oxygen together. The most stable state of carbon is graphite, or solid carbon, plus the most stable state of oxygen is O2 gas, and that yields carbon dioxide gas. And then you could look this up in a table, and here's a table down here of a bunch of standard enthalpies of formation. But for carbon dioxide, it's negative 393.5 kilojoules per mole. Say we wanted it for a ionic compound like potassium chlorate. So first you got to rip it apart into its elements. So you have potassium, its standard state, it's a solid. Chlorine, its standard state is a diatomic Cl2 gas. But you only need 1 here, right? So you have 1/2 times your chlorine. And then we need 3 oxygens, but oxygen standard state is O2, so you have to multiply it by 3/2. And this would be your equation to calculate the standard enthalpy of formation, which, if you look it up, is negative 391.2 kilojoules per mole. If you have an element in its standard state, its heat of formation is 0 because it was formed already. Okay? It's not like this element could be formed and it's in its standard state, so it is 0. So that's important to remember. So let's try this example. Remember, the heat of formation is for 1 mole of products being formed by mixing the elements of whatever's in that compound. So it says write the balanced chemical equation for the formation of calcium carbonate. So the first thing, we are forming calcium carbonate, which is a solid. What are the elements in it? Well, we have calcium, which in its standard state is a solid, plus carbon, which in its standard state is graphite, it's a solid, plus oxygen. In its standard state, it's O2, which is a gas. But I need 3 oxygens over here, so I have to multiply this by 3/2. And this would be my equation where I could get my heat of formation. So Hess's law. So when we were talking about doing the calorimeter problems, we were measuring delta H. But in order to measure delta H for every reaction, it's kind of inconvenient and time consuming. But luckily, according to Hess's law, you don't need to actually do every reaction to measure the delta H. As long as you have the delta H for reactions that will kind of build up and make your final reaction, then you could just add up the delta H's for each of those reactions. So we can estimate our delta H using published values in data tables. There's a data table in your book and in the appendix. So some important things to remember is the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes of each individual step. And remember, enthalpy is a state function. And if you forgot what that means that it's independent of the path. So you could just get your final enthalpy minus your initial. So some rules to follow. If you reverse your reaction, you have to reverse the sign of delta H. If you multiply your chemical reaction by a coefficient of some sort, then you have to multiply your delta H by the same coefficient. So what am I talking about? Well, here's an example. Here is the equation for the formation of methane. And I would like to find the heat of formation of methane. So you don't have a data table, but you are given these 3 reactions and told that by maneuvering these reactions in a certain way, you can form the reaction up on top. So it's sort of like a puzzle. First thing you want to look at here is you need to get methane as a product. So is methane in any of these reactions here? Yes, it is right here. But it's a reactant, so it's on the wrong side of the equation. So what we have to do is flip this equation and write it in reverse. So that's what I did here. I have CO2 plus 2 waters yields CH4 plus O2. Because I flipped the equation around, I have to make my negative 890.8 positive. This is because I flipped the equation. So now we have our product on the right side. We have it as a product. Next, I need to get hydrogen on the left side, and I need 2 of them. So hydrogen is already on the left side, but how many of them are there here? There's only 1. So I need to multiply this whole reaction by 2, and that's what I did here. See that? So because I multiplied my whole reaction by 2, I need to multiply my delta H by 2. So now we are ready to add these 3 reactions together. So you see here, I multiplied by 2. This one down here, I flipped it so it became positive. And the one in the middle I could leave the same. So now you're going to cross out the elements that appear opposite of each other. So take your 2 waters. So you have 2 waters on the right and 2 waters on the left, so they go bye-bye. You have a carbon dioxide on the left and 1 on the right, so they could go away. Here you have 2 oxygens, and you have 2 oxygens over here. So what are you left with? When you bring it all down, isn't that the reaction that you wanted to get? So then, because whatever you did over here in your chemical reactions, you did over here to your delta H's, you can add these up, and this would be your heat of formation for that reaction. It's actually kind of fun once you get to play around with it. It's a little bit of strategy and puzzle solving. Okay, so Hess's law basically states that the enthalpy difference between the reactants and the products is independent of the path. So you could have as many of these reactions as you want, as long as when you add them all up, you get the reaction you're looking for, then you should get the right delta HF that you're looking for. A shorter way to use Hess's law, instead of writing all this out, is that you could take the heat of formation of the products, so in this case it would be methane, and N is the number of moles in front of it, so in this case it would be a 1. 1 times the heat of formation of methane, minus the sum of the heat of formations for each of these elements. Okay, in this case it would be kind of hard to do it in this way because the heat of formation for carbon in its standard state is 0, and the heat of formation for hydrogen is 0, and you don't know the heat of formation for methane. That's why we kind of had to do it this way with the reactions. And these are 0 because they're elements in their standard state. So let's use this example and the shorter way so you can see how to do that. So you're going to take the sum of your heat effusions of your products, but the number of moles you have of each product times it. So let's look. What are our products? Here are our products. So I have 3 carbon dioxide. So 3 moles times the heat of formation for carbon dioxide. That is what is shown here. And I have 4 waters. So 4 moles times the heat of formation of water. Minus the products. So here are my products. So minus, you're minusing the products. So here I have 1 C3H8, so 1 times the heat of formation of C3H8. And I have 5 oxygen, so 5 times the heat of formation of oxygen. You look in the data table that's in your book, or it's in the appendices of your book, and you could get the heat of formation for each of these values. So the heat of formation for carbon dioxide is negative kilojoules per mole. The heat of formation of water. And it's important that you look at the states that it's in, because liquid water has a different heat of formation than gaseous water. So you have to make sure when you're using the table you look up the right number. And the heat of formation for C3H8 is equal to, and the heat of formation of oxygen, oxygen's an element in its standard state, so its heat of formation is 0. Now notice the units here are kilojoules per mole. That mole goes away because you're multiplying it by the number of moles here. So then when you do all that and add it all up, you get your heat of formation here. So let's try to calculate the heat or the enthalpy of the reaction that's above. And we are given these 3 reactions to kind of build on. So we can maneuver these reactions in some way to build our final equation. So I did it both ways, the long way and the short way here for you. So let's look at the long way first. Remember, here are our original reactions. I put them here for reference. So for the first one, my final reaction has carbon dioxide as a product, and the first reaction has carbon dioxide as a product, so I leave it alone. Okay? Then I need sulfur dioxide as a product, but originally I had sulfur dioxide as a product, but only 1 mole of it, but I need 2 here. So because of that, I have to multiply everything by 2. So since I multiplied my reaction by 2, I had to multiply my delta H by 2. Finally, I need CS2 as a reactant. Originally, it was a product, so I need to flip this equation over. So I flip it over, and by flipping it over, my plus 87.9 becomes minus 87.9. So now I check, and my carbons go away, my sulfurs go away, and I end up with the reaction that I wanted. So then I could just add all these up, and this will be the enthalpy of the reaction. So that's the long way. The short way, remember, you're going to use the sum of the moles times the products minus the sum of the moles times the reactants. So my products, here are my products. So I have 1 mole of carbon dioxide, and here the delta H for that reaction is negative 393.5. So I put that in there. I have 2 moles of sulfur dioxide. This is the amount for 1, so I have to multiply it by 2. Minus, this minus is very important, the sum of the products. So I have 1 CS2, and to make 1 CS2, it's 87.9. And oxygen in its standard state is 0. And when I do all that, I will get the same answer that I got doing it the long way. All right, let's try this example. So here I have the equation for forming 2 moles of water and forming ozone from oxygen. And I want to create this reaction right here. This is the final reaction that I want to get. Okay? So I need to rearrange my equations here so that I could build what I want over here. So first, I need 3 moles of water as products. So this equation here only has 2 moles. Okay? So I'm going to rewrite this. And my delta H for this is negative 483.6 kilojoules. So in order to get 3 moles, I need to multiply this whole thing by 3/2, right? The 2's will cancel out, and I'll end up with 3 waters. So whatever I do to my reaction, I have to do to my delta H. The second reaction, my ozone's on the wrong side, so I need to flip it. So now it becomes negative because I flipped it. But I need only one mole over here. So I need to multiply this whole thing by 1/2. And now if I check this out, I'm going to end up with 3 waters. And my O2's go away, 3/2 and 3/2 go away. And I end up with 3 hydrogens plus 1 O3. Okay, so then I add these up and I get my delta H of the reaction is negative 867.7 kilojoules. So let me write that here so you can see better. This is your enthalpy of the reaction. All right, so now let's do this one here using the shortcut method. Remember, our delta H is equal to the sum. This squiggly thing means sum of the number of moles times the delta H for the products minus the sum of the moles for the delta H of the reactants. So let's look at our products. So I have 12 carbon dioxides. So 12 times, I look here for carbon dioxide. Negative 393.5 plus 6 gaseous water vapor. So I'm going to use this here. So that's all of the products minus the reactants. So my reactants, I have 2 C6H6 which is benzene. Nasty chemical. So 2 times 49.0 plus 15 times oxygen, which is 0 because it's in its standard state. So when you multiply and add, you get this would be the heat of the reaction. So delta H of the reaction is negative 6,271 kilojoules. So that's nice for the reactions, but what if we could take it down to even a simpler thing? Breaking bonds. When you break bonds, you have to put energy in, and when you form bonds, energy is released. So let's look at this for covalent bonds. What determines the strength of a covalent bond? The bond enthalpy, or how much energy is required to break the bond. The amount of energy required to break the bond tells you the strength of the bond. The higher the amount of energy to break a bond, the stronger the bond. And double bonds are stronger than single bonds, and triple bonds are stronger than double and single bonds. Okay? So here's a picture of it. So my bond enthalpy is the amount of energy you need to put in to break a bond. If you're putting energy in, what sign is that? Is endothermic. So it is positive. You're putting energy in. So I want to break this bond. I put energy in and I break it. I want to break these 4 bonds. I put energy in and I break them. The amount of energy I'm putting in is my bond enthalpy. So here's a table that's from your book of average bond enthalpies. Remember, your bond enthalpy is always positive because energy is required to break chemical bonds. So it's always positive. When you form a bond, when you're forming bonds, energy is released. So that is negative. The greater the bond enthalpy, the stronger the bond. So just looking at this table, let's see, what is the strongest bond? Well, so far it's this carbon double bonded to oxygen. Yep, this one here is the strongest bond. So bond enthalpies and enthalpy of a reaction. So when you want to calculate your enthalpy of a reaction just from the bond enthalpies, you have to add all the energy for the broken bonds. And then you subtract the energy released from bonds being made. You sum them all up and you get your heated enthalpy of the reaction. So you want the sum, remember this sign here means the sum, of all of the broken bond enthalpies. So broken bond enthalpies. And where are the broken bonds coming from? They are coming from the reactants in your chemical reaction. Then you want to subtract the sum of the bonds formed. And these are in your products. So reactant bonds will break, product bonds will form. Not to be confused with Hess's law. Hess's law had your products minus your reactants, okay? So let's do an example of this. So here's a picture. Here I have methane plus chlorine gas. And in the end, I'm going to form this compound. So So in order to get my methane, to get rid of a hydrogen and bond with the chlorine, I have to break one CH bond. I have to break this bond. So one CH bond has to be broken. And then I also have to break one chlorine bond has to be broken. So let's sum up the energies required to do that. So here I have, these are the bonds that are broken. And these are the bonds that are formed. So I look on my table, I look for CH. It's 413, and I look for chlorine bonded to chlorine. Where is that? That's 240. Minus the bonds that are formed. So here, this bond was formed. That is a bond between carbon and chlorine. So I am forming a carbon and chlorine bond and a hydrogen and chlorine bond. One of each of those. So I look up carbon and chlorine. So minus 328 plus hydrogen and chlorine, 431. Calculate all that, I get my heat of reaction. That is just from the energy to break and form bonds. Okay? Kind of powerful if you think about it. Well, that is the end of chapter 5.